Hello, my name is Matthew Nolan, and this is video 4 for homework assignment 2. And in this video, we're going to be using Cardano's formula to write a Python function to calculate the specific volumes given for pressure and temperature for the SRK equation of state. Before we start coding, I want to clarify one thing before we start. In part 1 of this homework assignment, we made a cubic equation using Cardano's formula. Using an equation of state. So what we want to do here, or the first two parts of our homework assignment, what we want to do here is set up a function that is in the form of this basic cubic equation, and then following the various steps of identifying a Q value and R value, and then going down the list and finding our individual roots here, and then going through the various parameters that this function will have us do. So from here, we will then split our screen to have our code up on one side and our information sheet on the other. So what we want to do is define a function called our cubic roots. We're just going to set it as R. And then we're going to have three variables we want to call later on. Next thing we want to do is then we're going to start with writing down our Q values and our R values. So from here, we're then going to set our Q values as such. So we have something being divided by 9. So we're just going to set that immediately. And then we're going to have our A squared value all separated off, and then we're going to have our B value multiplied by 3. And this should be good. Excuse me, we need to separate this off first. Excuse me. Next thing we want to do is then separate, is to make a R value function. So here, we're going to separate this off and have our 54 being divided by our top values. So then we'll have our first function here is going to be our A values. So it's going to be A times 2. And since that's being cubed, we're going to we're going to separate that off once again, just to separate off from everything, and we don't get any overlapping. Or we don't want that 2 multiplying our A value immediately off the bat before it gets cubed. That will mess up some steps later on. So what we want to do from here is have our next value written down, which is going to be our 9. So it's going to be 9 times A times B. And we will once again separate that off and do our C value. So it's going to be 27 times C. So it looks good so far. Next thing we want to do here is then set our theta value. And from here, there's one little thing I almost forgot, is that our R and Q values play a big role on what we do for the rest of this equation here. So if it says that our R value squared is less than our Q value cubed, then it has 3 real roots, and then we can start going off and doing that. So what we want to do here is set a if or then statement. So we want our R value less than our Q, and then we can write our theta value equals our numpy function of our cosine of R divided by a cubic root. So that will be Q to the power of 1/3. So that's separated off into one separate equation, and then we can start using our roots down here, or start solving for them. Next, we want we're just going to set a value that's going to call all 3 of our or going to solve all three of our roots at the same time, so we don't have to mess with it too much. So what we're going to do here is set our roots function. I'm going to do -2 multiplied by our q, which will then be, or we're going to separate that off, so now our q value to the square root, have that separated off, and that will be multiplied by our numpy function of cosine. And from here, we're going to do something a little funky. If you notice that our theta values, all in this middle section here, all of these theta values in +2 pi and our -2 pi are all being divided by 3. So what we can do here is just have this entire function be multiplied out in this cosine cosine function. So what we want to do here is set our theta values. So we're going to start with our x1. So if that script will go away for me. So it's going to be theta divided by 3, and then it's going to be our theta value plus sorry, I don't like when that text shows up. So then that will be our second parameter, x2 parameter, so it's going to be theta plus 2 pi 2 times our numpy function of pi, and then that will then be separated off one more time. Before we go any further, we want to have that divided by 3, and then since our x2 and our x3 have very similar values to it, we're just going to copy and paste this little tidbit over to the other side. Have that divided by 3. And then we'll change that. That theta plus 2 pi will then be changed to a minus to fix the rest of our x3 variable. So then we'll close off that. We're going to close off that array, and then after that we will have our last a divided by 3 over there. So these are our real roots for this. So from here, next, what we want to do is then set our return function, which is going to be np.sort, and it's going to be our roots. So then we'll have that separated off. However, we have to set another if function. Then we'll set our else function, which will then include our non-real roots, or our other roots of a and b down here. So what we want to do here is then start with our a value, which will then be our numpy function of sine of r. And this sine function, or this actual sine function here that we're using in Python, or in Code Laboratory, excuse me, this is just going to give us either a -1 or a 1. It just wants the sine of r. So if r's -1 or a negative value, it will give a -1, and if r is a positive value, it would just give a 1. So what we want to do here is then separate another equation off, which will then have our absolute value of r plus underscore, excuse me, then have then our square root in here for the r. So then we'll have just set one thing up here. Just not to do confusion, so we'll do start with our r value. So it's going to be r squared minus our q value cubed, and then that whole thing separated off from each other. And then what we want to do from here is then have it going to the square root. So that whole thing is separated off. And then what we want to do from here is then have this whole absolute value plus the square root function. What we want to do from here is then have that be taken to the square root. So that will be 1 divided by 1 over 3. And just make sure there's no conflictions with that first one. With our multiplication up there, we're just going to be extra cautious. So we're going to then put our sign there. Well, it looks like I have one too many parentheses somewhere. There it is. Wow, I really messed something up here. Sorry, let me just rewrite this real fast. Not sure why I'm struggling with this, so it's just going to be absolute value of r plus our r cubed minus our q value, which is cubed. We're going to separate these two things off. Sorry, I'm just trying to redo my work here. That's going to be to the 1/2. So make sure all the parentheses are correct so far. Oh. Okay, so that everything's correct so far. Then we want to separate that off, this whole function off together. So this is enclosing that. There we go. Okay. Now from here we can then put another parentheses here, then put another parentheses back here. Or wow, I already had that one there. That's what my problem was. Sorry about that. And then that will have our 1/3 enclosed in it, and since we have a thing there, then we can have our closing parentheses wrapping this whole thing up together and having it multiplied by our sine of r. Next we want to do is set our b value. And if you notice here is that we have to set another if or else statement, which will then carry out the rest of our function. So what we want to do here is then set the rest of our function. So then b, we're just going to set b equal to 0 originally, and then set our another if function if a is equal to 0. And since we're not calling or giving a value, we just want to use it as a parameter in our if-else statement. So we're just going to use two equal signs here, and then say if a is equal to 0, then we'll use our else statement here, and then we're just going to use q divided. And then we can return our final value, which is going to be our a plus b, and that will be our a divided by 3, or negative a divided by 3. Okay, that should be running good. The next thing we want to do here is then set our Cardano equation that we got from parts 1 and 2, and then set it to our cubic function that we have here. So the next thing we want to do is then start drawing information from our sheet that we used in part 3 to find our isotherms from up here. So we need to draw a couple functions. So we're going to define another cubic function. So it's going to be cubic. We'll just do our cubic volume, and then we're going to use it. And since we want to draw our pressure and our temperature values from our SRK equation state, we're going to set that as our draw functions. And what we want to do immediately off the bat is then come up here and take our cubic C values from here. We want to take our cubic C function and set that equal to our return values here. So we're going to come back down here, copy and paste that, and set our values that we want are a, comma, b, comma, epsilon, and sigma equal to our cubic function that we have up above. Just to make sure everything's in order. Okay, AB epsilon sigma. And then we can then recreate our beta parameter and our Q parameter that we found in our, when we first derived our cubic equation for our equation of states. So what we want to do here is take our beta value. So we're just going to say beta is equal to our B value times our pressure, and that will then be divided by, sorry, I'm missing the keys here, our gas constant times our temperature. And then our Q value can then be set as our A value divided by our B parameter multiplied by our gas constant times our temperature. Voila. Next thing we want to do is then set A value equal to Z. And if you remember from our original equation is that we set our Z, our compressibility factor, as our sort of our pseudo X value that has our roots connected to it. And since we have a root solver up here to find our roots of our equation, we're going to just copy and paste this down here. But instead of using A, B, and C, we're going to set our parameters that we found from our first part. And if you can see from here, we have our parameters here. Our Z cubed from our normal cubic equation doesn't have a coefficient or a root that goes along with it. So we're going to immediately start with our Z squared value. So we can then set our Z squared value as such, which will then be our epsilon value plus that sigma value. I'm going to shorten this because it's going to get very long. Our sigma value multiplied by our beta value. Sorry. And then since these are all the same roots, they're going to get added all together. So then we'll have minus our beta value minus 1. Sorry, I'm just going to clear the space here because this is going to get messy very quickly. And we're going to put a comma. And we now want to set our next function, or not function, our next root is our Z value. So what we want to do here is then set our next values, which is now our epsilon value times our sigma value times our beta value squared. So we're just going to do it again. After that, we will then have this next function here set. We'll separate that off with parentheses. So it's going to be our beta value times our beta value times our epsilon value plus our sigma value. If that, we'll separate that off again. And then we'll go on to our next function, will be our epsilon value plus our sigma value. And we'll have that whole set multiplied by our beta value times beta. And then we'll have our next thing set by our Q value, which we have up above. And then be our Q multiplied by our beta value. Separate that off. And then we're on to our last root, which is our just normal coefficient, our C value. So is that off? Separate off, so then we can, I'm not sure why it's going wonky on me, so we're just going to do another refresh. And then we'll have our negative epsilon value multiplied by our sigma value times our beta value, which is cubed. So we're just going to do this as such, our beta value cubed. And then we'll have our have this next thing separated off, which is our epsilon value times our sigma value times our beta value. Ooh, that's nice, beta. Our beta value squared. That's separated, and then we will have our final portion of this equation then be separated by a q. Separate that off just for a quick second. Our q times our beta value squared. So then b times beta, and voila. That is, ooh, there's something wrong here. I did not mean to put that like that. So that is going to that, and this one is going to, I figured out another problem I accidentally did there. I didn't want to do that. So that's good. And then that's going to finish off our cubic roots equation. And from here, we can then return our function. And since we're trying to find the volume of our SRK equation state, we can then come back down here. Have it somewhere, there it is. And then we can then return our function of z, gas constant, temperature, and pressure, since we have all of these parameters being put in right now. We can then return our function as such. So we're going to have our z value multiplied by our gas constant times our temperature divided by our pressure. Not syntax. What did I do? We don't want that there. Try that again. There we go. Okay. And then we can call this function to make sure everything is working properly. So let's just give a random pressure value. Since our pressure value is going to be pretty high, we'll go 1 to the 6th, and then to the power of 6, and then have a temperature value of 300 Kelvin, just to give what we want here. I did something wrong here. I probably had a misplaced. Oh, I see what I did wrong. I had to have a beta value get multiplied, so hold on. I'm just going to go back and check so I don't have another one of these mistakes before it starts yelling at me again. So it looks like everything should be fine. So it should be fine. And that should be fine. Ooh, and we're getting 3 numbers off. And we're getting 3 numbers right now, which means our entire function is then working as intended. Since we have 3 values, we now have an A, B, and C parameter to plug in to the rest of our equation.